Hello everyone, I am Dr. Fawzul. I am giving some series of lecture for the course Probability and Statistics. So in the previous lecture, we have started with our continuous random variable. We discussed the probability density function. We discussed their cumulative distribution function, right? And we also have seen that their relationship. Like if your PDF is given, how to find the cumulative distribution function. And in today's lecture, we'll start with the other way around. That suppose your cumulative distribution function is given for a continuous random variable, how you can get the probability density function, right? So let us start with some example. We have seen last class that last video we have seen that you can just have to derivative it. Once it is differentiable, the cumulative distribution function, so you have to derivative it, you will get the probability density function. So for this example, it is very easy. The cumulative distribution function fx is given. If x is less than 2, it is 0. If x greater equal to 2, it is 1 minus 4 by x square. So let us do shortly. So if you have x is less than 2, then your probability density function small fx is equal to that f dash of x, but f dash value is 0. In this case, capital Fx value is 0, therefore this value is 0. And if you have x is greater than or equal to 2, then your fx is equal to that f dash of x, but in this case f dash is 1 minus 4 by x square, so it is d dx of 1 minus 4 by x square. And if you do the derivative, it's a very easy one. And if you do the derivative, you will be getting the answer as this is 0 minus 4 into minus 2 into x to the power minus 3. So it is 8 by x cube, right? And therefore the probability density function finally, it's a piecewise defined function, 8 by x cube whenever you have x is greater or equal to 2 and equal to 0 otherwise. So this is the probability density function. So this is an example where a cumulative distribution function is given and you can easily find its probability density function. Okay, so let us move to the next problem. Yeah, this one already we did. Let us do one more example, and here not only you have to find the probability density function, you also have to plot its graph, right? So this is again this is very easy. So I am not directly I'm doing that fx value is what. So if you have x is less or equal to 0, then its derivative is again 0. If capital Fx derivative is again 0, so this value is also 0 if you have x less or equal to. If x value is between 0 and 1, the derivative is 1. So whenever you have 0 less than x less than 1. And this is again 0 if you have x is greater or equal to 1, right? So in short, you have in two places x less than or equal to 0, it is 0, and x greater or equal to 1, it is 0. So I can simplify this and I can get fx is equal to 1 if you have 0 less than x less than 1 and equal to 0 all other cases otherwise, right? So this is the probability density function. And if you want to plot its graph, how you have to do? So you can see that this plot is very easy. Between 0 to 1, it has value 1, right? So between 0 to 1, it has value 1. In all other places, the value is 0. So basically, this is the function. In all other places, the value is 0. From there onwards, this value is 0. So this is the point 0, this is the point 1, and this height is also 1. And later on, we'll see that it is actually a uniformly distributed function. We'll discuss about it later in some other video. Okay, now, yeah, this one we already did. Now, in discrete type random variable, we have defined the mean or expected value of the random variable, variance of its standard deviation, right? And similarly, we can define the mean or expected value of a continuous random variable. So if x is a continuous random variable with probability density function fx, then its expected value is equal to minus infinity to infinity x fx dx. right? Whereas in case of a discrete random variable, what we have seen, it was summation of, in case of a discrete random, it is summation of x px, right? X into p of x, if you remember. But here it is a continuous type, so you have to do the integration, and integration over the whole possibility, so minus infinity to infinity x of x dx, right? And expectation you can also denote it by mu. So once your expectation is defined, you can find its variance. So the variance or the sigma square, you can denote it. It is minus infinity to infinity x minus mu whole square fx dx, right? Where this x minus mu whole square fx dx, mu is the expectation. So in this way you can define, and then we know one working formula how you can find the variance. In this case also it is the same. It is expectation of x square minus expectation of x whole square, right? So mean and variance different definitions are almost similar, but in this case it is the integration instead of summation. And then the standard deviation, which is the root of square root of the variance. So therefore it is sigma is equal to root over of variance of x, right? We'll do a couple of examples that how to find the when the probability density function is given and you have to find its expectation, variance, standard deviation, like that, right? So these are very easy kind of thing. Only we will be doing uh, some working exercise. See, for this example, let x probability density function is given for the continuous random variable x, if x equal to 2x, between 0 and 1 equal to 0. Otherwise, what is the expectation? So just a, a simple integration. So expectation of x is equal to minus infinity to infinity x fx dx. But fx value is 0 all the places except between 0 and 1. So our integration is only will have some value between 0 and 1, x into, and in this case fx value is 2x into dx. In all other places it is 0, so we are not at all considering. And therefore 2 into x square dx, so to 2 into x cubed by 3, if you do the integration, and you'll get between 0 to 1, so this value is 2 by 3 into 1 minus 0, so therefore it is 2 by 3. So in this case the expectation is 2 by 3 for this random variable. Clear? This is a very straightforward example. So we have done it very first. Now let us do one more example, which is a good one. See, the density function is given as it involves some exponential function, right? So 1 by 4x e to the power minus x by 2. Whenever x greater than 0 equal to 0 otherwise. So in this case, let us find the expectation. So how to do the same way? So expectation of x is equal to, so minus infinity to infinity fx fx dx. Maybe I'll write minus infinity to infinity x fx dx. But here fx is value only between 0 to infinity. Otherwise it is 0. So we'll consider 0 to infinity x into fx value between 0 to infinity is 1 by 4 x e to the power minus x by 2 dx. And therefore it is equal to 1 by 4 into 0 to infinity x square e to the power minus x by 2 into dx. Now how to do this integration? Yes, we know that it is the we have to do the integration by parts method, right? So here one algebraic function and one exponential function is there. Definitely you have to take this x square as a first function. So how to do? Take 1 by 4 as common. I'm taking it outside, and then that x square is outside, and integration of the second function. So integration of e to the power minus x by 2 dx. And of course, you have to do after this, you have to do the integration between 0 to infinity. Minus, you have to do another one, that overall integration of maybe the integration limit, we'll do it at the end, right? We'll write down the integration limit at the end. Okay. So x square, derivative of 2x square, which is 2x, into integration of the second part. Shall I directly do? Okay, integration of this part is what? E to the power minus x by 2 divided by minus 1 by 2 into dx, and limit between 0 to infinity, right? And then if you do it, 1 by 4 into x square into, again if you do the integration of this, what will happen? So minus 2 because e to the power minus x by 2 by minus 1 by 2, so this will become minus 2 into e power minus x by 2, limit between 0 to infinity, minus this will become minus and minus become plus 4 into 0 to infinity x e to the power minus x by 2 dx. Easy. Now if you put the limit, if you put x is equal to infinity, then e to the power minus x by 2 will give you 0, and if you put 0, then this x square will give you 0. So the first part of this integration is actually 0 once we put the limit, right? So plus I have that 4 into this quantity, this 4 into integration of this quantity. So what we'll do, maybe plus 1 by 4 I had into 4 into 0 to infinity x e to the power minus x by 2 dx. Now again, what you have to do? You have to do the integration by parts, right? So take this x as a first function, and the take x as a first function, and don't I have space? Okay. So this part as a first function will do what we'll do. So this part is 0 and this has become 1. We only have 0 to infinity x e to the power minus x by 2. So I'm just directly doing x into by parts of this. So this one is keeping it and integration of this part. So minus 2 e power minus x by 2 between 0 to infinity minus derivative of, so integration, first of all integration will be there, 0 to infinity derivative of x, which is 1, into integration of this, which is minus 2 into e to the power minus x by 2 dx, right? And then now what will happen if I again put the x is equal to infinity? This value will give you 0, and if I put the limit for 0, this value will give you 0. So this integration value is 0, and this will become plus 2 into 0 to infinity e to the power minus x by 2 dx. So this one again, if you do the integration, e to the power minus x by 2, so 2 into minus 2 e power minus x by 2 between 0 to infinity. So infinity value will give you 0, and 0 gives 1, so minus 0, so therefore it is minus 4 into 0 minus 1, therefore this value is actually 4, right? So this is a expected value of this random variable is 4. So this is again easy one, but it involves the integration by parts. So now onwards you have to recall all your integration formula, whatever you have learned in your plus 2 level or in calculus course, right? So do practice few examples of this integration because it involves a lot of integration, right? Okay, let us move to the next problem. Yeah, this one we already did. So the solution was 4. Now we have one more example, which is this one. Just a minute. So look at this example. The density function of x is given by fx is equal to a plus. So the probability density function is given and its expectation is also given. Expectation of x is 3 by 5. You have to find the variable a and b. Now this kind of example, we may have done it in our calculus courses. So you have two unknown, right? A and b. So you need to have two equation to solve it, right? So what we can do it here, we have two condition as well, right? We know that probability density function, the total sum is 1. Why don't we apply that? So integration minus infinity to infinity fx dx should be 1, right? And therefore it is between 0 to 1 only, it is some value. So therefore this integration will become 0 to 1 a plus b x square into dx should be 1. And if I do the limit a into x dx, so it is actually a plus bx square, so b into x cube by 3. And if I put the limit, it is a plus b by 3 is equal to 1. So one equation I got it from using the probability density function. Now another condition is also given. Expectation is given as 3 by 5. So let us apply that. So E of x, expectation of x is equal to 3 by 5. So if I apply this condition, what will happen? Again, that means integration minus infinity to infinity x of x dx, but it is valid between 0 to 1. So x into fx value is a plus bx square dx. This is equal to 3 by 5. Now this value is, if I do the integration a into x dx, that means a into x square by 2, right? A into x square by 2 dx, and x square by 2, if you do the put the limit between 0 and 1, so it will be a into 1 by 2 plus b into x cube dx, that means x to the power 4 by 4 integration. After doing the integration, b into x to the power 4 by 4, and if you put the limit 0 and 1, it will become b into 1 by 4. This is equal to 3 by 5. So equation 2. So I got two equations. I have two unknown a and b. Now if you just solve a and b, if you just solve equation 1 and equation 2, you will be getting the answer. So solving 1 and 2, we get a is equal to, so if you just calculate, I am not showing you the calculation, you can do it very easily. A is equal to 3 by 5 and b is equal to, you will get 6 by 5. Right? So we got the solution for this two parameter a and b. Okay, now this example we have done. Yeah, that one we have already seen the solution, and the final solution is a is equal to 3 by 5 and b equal to 6 by 5. Okay, then we have one important theorem related to the expectation. So if x is a continuous random variable with probability density function small fx, then for any real valued function g, expectation of gx is equal to minus infinity to infinity gx fx dx. Now this kind of theorem we have seen for the case of discrete random variable as well, right? So while calculating, so expectation of gx was, it was gx into px, summation of that. So the similar theorem, analogous theorem for the continuous random variable. So for any real valued function, its expectation you can also calculate, that just in place of x you will have gx fx dx to get that thing. And if I apply this thing, then expectation of the ax plus b is actually minus infinity to infinity. Now this is works as gx, so ax plus b fx dx, and if you simplify it, you will basically see that it is aex plus b, correct? So it is kind of a linear type. Now from this theorem we can say that expectation of a into x is actually what? A into e of x. And expectation of any constant value is what? E of b is what? It is actually this constant value b itself. Right? So with, if I just directly apply this theorem, we'll be getting these two results. Okay. Now move. Just do one applications of this previous theorem. What is given? On fx is given, you have to find the expectation of e to the power x. So this is very, very easy. So it is actually equal to 0 to 1 e to the power x fx dx. Although the integration is between minus infinity to infinity, but fx value is 0 except in the interval 0 to 1. So we'll consider only between 0 to 1. So this value is actually 0 to 1 and e power x dx. Very straightforward integration. So e to the power x between 0 to 1. So it is e minus 1. We got the answer. Easy. Okay, let us move to the next example. Yeah, this one we have already solved. We have one more example. Certain coded measurement of the pitch diameter of thread of a fitting have the probability density function fx equal to this value. Again, you have to find the expected value of this random. That again, very easy kind of problem. So if x is given, what is the expectation of x? So it is between 0 to 1 x into fx dx. So 0 to 1 4x, that means 4x by pi into 1 plus x square dx. Now this integration again, say when the numerator 1x term is there, I need to have the derivative of 1 plus x square, so I can easily accommodate. I'm just taking 2 by pi out, then 0 to 1, then 2x dx. But 2x dx I can write it as d of 1 plus x square divided by 1 plus x square. So now this is a very standard one. It is dx by x type. So what is the integration formula? 2 by pi ln of 1 plus x square. And it has limit between 0 to 1. So therefore, if you put the limit, it is 2 by pi into ln of 2 and minus ln of 1 is 0. So therefore, the answer is 2 by pi ln 2. Right? So this example. So I'm going little fast because these are very straightforward and easy kind of example. But what is my suggestion? Please do practice lot of integration in these cases, because this chapter and the another next unit is again involve lot of integrations. So please do practice some integration problem like this, or you can just recall in your plus 2 level whatever integration formula you have learned, that thing you please recall. Okay, so this one we have already done this example. Now this is one interesting problem. A stick of length 1 is split at a point U having density function fu equal to 1, and whenever you have 0 less than u less than 1, right? A stick of length 1. I have a stick of length 1. Now it has a split at a point. So in someone it has a split at a point u. And this u has a density function fu equal to 1 between 0 and 1 equal to 0 otherwise. Now determine the expected length of the piece that contains the point P. Now you have to determine the expected value of another random, right? What is that? That is the length of the piece. Length of the piece. That means that the because it was splitted. Now the previous one, the length of stick 1 was splitted. Now you have to find the expected length of the piece that contains a point P between 0 and 1. Correct? So how you can do this problem? Uh, we'll do it. Let we define a new function LPU denote the length of this piece, right? Denote the length of the substick maybe that contains the point P. That contains the point P. So we define a new function. So which is denote the length of the that substick which contains a point P. Now let us understand this situation through some that graphical notation. So I initially have a stick of length 1. So between 0 to 1 I have a stick of length 1. And I have a point P in it. Right? I have a point P in it. But this stick is actually splitted somewhere. So it can be splitted in any places, right? It can be splitted in any places. Maybe it is splitted here. It may be splitted here. We don't know. It may be splitted here. It has one split, and that is its density function is given as u, right? So we don't know. So depending on where it got splitted, depending on that, we can get the length of the stick, right? Whether uh, length of the stick that contains the point. So suppose if it's splitted somewhere here, maybe here, if it's splitted here, that means in these places, then what is the length of the piece that contains the point B? So in this case, this is the piece, right? In this case, this is the piece. It contains the point P. And what is the length of it? Correct. So its length should be 1 minus P, because the total length is what? 1. And it is splitted somewhere here at the point U. So what is the length of this portion? It is 1 minus U, right? So therefore, we can write the LPU function here as LPU is equal to actually 1 minus U. The length of the stick is 1 minus U whenever U is before P, right? That means whenever U is less than P. Because here 0 to 1, this is U length is this one and P is more, right? So if U is less than P, you will get LPU value is this one. Now you may have a situation where the length was that was the stick 0 to 1 and P point is the same place here, but it was splitted somewhere here. So in this case, what should be the length of the piece which contain the point P? So in this case, actually this portion you have to get the length, right? This is the portion where you have to get the length. Now what is the length of this side, this portion? Definitely it's like u only, right? Because this length is u between 0 to u. So this is u. And when it is the case, if you have that u is greater than p. Clear? So initially we had a probability density function for u, which is fu equal to 1, which is 0 less than u less than 1 in that case, otherwise it was 0. And we got a new function LPU, which depends on the p value, and it is that piecewise manner it is defined. You have to get the expectation of this function LPU, right? This is the length of the piece that contains the point P. So you have to get the expectation. So let us calculate the expectation. So expectation of LPU. Now again we know the theorem, expectation of gx is minus infinity to infinity gx fx dx. We'll apply the same thing. So it is minus infinity to infinity. Then we'll just simply do LPU fu du. Now this has two defined. So LPU is defined between 0 to 1 and FU is defined between 0 to 1. So I'll start from 0 and up to P, the value is up to P U value, the value is 1 minus U. So it is 1 minus U. FU value is always 1 into 1 du plus I have from P to 1, that LPU value is actually U and FU value is 1 into du. And after that it is a simple integration. If you do the integration, it will become a 1 du, that means u minus u square by 2 between 0 to t plus u square by 2. The integration is between p to 1. Now if you just simplify this, it is p minus p square by 2 plus 1 by 2 minus p square by 2. If you do the calculation after simplifying, you will get it is 1 by 2 into plus p minus p square. So this will be our answer, the expected value. Clear? So this is very important one and very interesting problem. It is little bit different than the other problems. I hope you understand. It's easy. Okay. This is what the solution that we already calculated. Okay, now let us do two examples of variance calculation. The variance calculation is just a simple integration calculation we can easily do. So this one, maybe you can take it for, or maybe I'll show you the just a solution. I'll solve a one interesting one. Right, so this one fx is given, you have to find the variance. So first you calculate e of x, then e of x square, then variance is ex square minus ex whole square. So finally you'll be getting the answer is 1 by 18. So but you please solve it. I want to solve a another example, which is this one, which I feel it's a good one. So your fx is given like that. You have to first prove that expectation of x to the power r is some value. Let us do this example first. So the part A is expectation of x to the power r. So it is minus infinity to infinity x to the power r fx dx. But fx value is between 0 to 1, so I have taken 0 to 1 x to the power r into fx dx. Now fx dx value is 2 into 1 minus x, so it is 2 into 1 minus x dx. Now let us do the integration. It is between 0 to 1, 2 you can take it out, x to the power r minus x to the power r plus 1 dx. And now it is very straightforward integration. X to the power r integration is x to the power r plus 1 divided by r plus 1 minus x to the power r plus 2 divided by r plus 2, and limit is between 0 to 1. And therefore this value is 2 into 1 by r plus 1 minus 1 by r plus 2, because 0 will gives you 0. And this is actually equal to the given quantity. Maybe what I'll do, yeah, this value is actually equal to the given quantity, which is 2 by r plus 1 into r plus 2. So the first part is done. Now next you have to calculate the variance of x. Now variance is what? Expectation of x square minus ex whole square. Right. So, but we know that x to the power r formula. So we can just put r equal to 2 and r equal to 1, and we can easily get the variance. So variance of x is equal to e of x square minus ex whole square. Now to calculate this one, just put r equal to 2 in the previous equation. So it is 2 by 2 plus 1, that means 3 into 4, right? 2 by 3 into 4. So 2 by 12 minus e of x is what? Put r equal to 1. It is 2 by 2 into 3. So 2 by 6 whole square. And if you just simplify it, you will be getting it is 1 by 8. Easy. And the part C is again the same way. We know that expectation of 2x plus 1 whole square is actually basically equal to 4 into e of x square plus 4 into e of x plus 1. Right, and e of x square value, e of x value, all these things, if you put, e of x square was actually 1 by 6. So 4 times 1 by 6 plus 4 into e of x was 1 by 3. If you just put r equal to 1, so it is 4 into 1 by 3 and plus 1. Again, if you just simplify, you'll be getting this answer is 3. Right? So, yes, this was the answer. This one, as we have done. Yeah, that's all for this lecture. I hope you enjoyed. So this lecture, what we did a lot of example we have solved. We have solved some interesting one as well. So for continuous random variable, we have checked that what is the mean, what is the variance, and we can did some example. So in the next lecture, we'll be coming up with some special type of continuous random variable. I hope you liked the video. So if these videos are really helpful, please give your feedback. I'll try to continue this. Thank you very much. We'll meet in the next video.